Okay, shall we start? We were talking about the forces acting on this rolling body, cylinder or sphere, and we covered gravity and the normal forces. Now we'll get into the more interesting one, the friction. So the friction, of course, is not acting in all the four cases that we'll be looking at. So we will start with, first of all, where it acts, like we did with the other cases as well. It's essentially at the point of contact, because that's where the normal acts as well. It's essentially some kind of a response to the normal when motion is about to begin or is already taking place. Right? So now it acts, of course, along the plane of contact. So it's a planar force in that sense. Of course, if the surfaces are having some kind of a curvature, then even then you're essentially looking at a small infinitesimal planar breakup of that distribution. So this will oppose the possibility of a slip, and that is essentially what is happening. We will look at, of course, four cases. We are talking more in generic terms right now. And like in all situations of friction, it acts opposite to the direction, opposite in direction to the relative velocity. So if there was no friction, and so what would have been the relative velocity between them? So essentially the frictional force is coming as an opposition to that. But as I said, there's this friction force acting in two ways, one of the body on the road and the other way as well. Proportional to the normal reaction, and that proportionality constant is what we call as the coefficient of friction, as you all very well know. So now coming to friction on rolling versus slipping, rigid body. So this is the distinction that we wanted to make in terms of what actually happens. And maximum friction force that occurs depends on the normal reaction. Mostly you would see that the static friction, of course, is larger compared to coefficient is larger compared to that for kinetic. And amongst that, the maximum friction force will depend on the normal reaction, of course, and the coefficient of friction between the two surfaces. And in fact, that happens to be the constant of proportionality, and we say F max is mu times m. And during the rolling, what actually happens is, with or without slipping, we will consider those cases separately later on. The magnitude of the frictional force is smaller compared to mu times m. So in the limiting case, of course, it can become equal, and you have rolling over there. During slipping, on the other hand, without rolling, you would have the magnitude of F equal to mu n. So essentially it's a range of F that we are talking about, starting all the way from frictionless when you have yes,
is that static or
this
rolling?
for rolling it's static. What you told was correct. So essentially you're looking at that point of contact, there is no relative velocity, right? So and this whole thing is based on the relative velocity, and therefore so during slipping without rolling, you have the magnitude of F equal to mu n. The reason why we are mentioning magnitude, because we are having an inequality over here, and we don't want to confuse when there's a positive or negative sign as to what we essentially mean about this. It's the size of the force that we're talking about. Okay. So now based on these two possibilities, one is an equality, the other is an inequality. Of course, a partial inequality, because equals is also a possibility over there. So we know that friction force if slipping, or have a kinematic constraint if rolling. So in the case of rolling, you're seeing that it's not necessarily an equal to sign. We'll have to investigate a little more to understand what actually it could be. Whereas in the case where if it is slipping, then you do not have an issue. And that was like a block, for example, let's say a rectangular block which was sliding down this, much easier to handle, because you already know your magnitude of F is equal to mu times m. Again, coefficient of static friction there too. So kinematics of rolling, this is something we covered in another class. We'll very quickly recap that, because we'll need some of those equations as starting points for understanding the kinetics as well. So there, of course, we were looking at a horizontal plane on which the rolling was happening, and was just therefore a point contact over there if it's a sphere, and a line contact if there is a cylinder, and that is maintaining itself in the horizontal plane as the body moves at an angular velocity theta dot, and the center of mass has a constant velocity which is in the x direction along the I hat direction, and these two are related, the theta dot and the velocity of the point C. In essence, what is actually happening is there's a particular shape that is being traced by this red point. Do you know what's the name of that shape? This point, if you let's say color this disk at a particular point on the rim, and then watch what happens to that red point, and you just trace it's when it goes through one full revolution, for example. Of course, after that it's periodic and it's going to continue repeating. Nearly. Spiral, yeah, it looks kind of like that, but it has a specific name that you can actually derive that equation mathematically quite easily. Where do you use wheels? The simplest place where you use wheels? A motorized, non-motorized transport that you use? What do you call that? Huh? No, which you ride by yourself.
I know the name, but I didn't know the history. Cycloid.
Exactly. That's right. Yeah. So it's not very different if you look at it from a layman's point of view, from a sinusoidal or a spiral. As you said, it's essentially a shape like this. That comes out. Yeah. So that's essentially what happens to it. That's besides the point. So assume the wheel has an angular velocity, because we're talking about a 2D problem here, irrespective of whether it is a sphere or a cylinder. Once again, I like to stress that, because many people think if it's a sphere then it has to be a 3D problem. Not necessary. It's essentially how the motion description is made in the simplest possible way, where you have only x, y translations and theta rotation about the z-axis. So you just have these three, and therefore it's a 2D, irrespective of whether it's a sphere or a cylinder. The angular velocity, therefore, in such a simple case is just given by theta dot k hat. In this particular case, we have introduced I hat horizontal towards the right, the j hat vertical upwards, and therefore the right-handed rule says that anti-clockwise should be positive. We have shown the theta dot to be clockwise, so that this will move in the horizontal direction towards the right, so that is positive. So the velocity of the center of mass is positive x direction, but theta dot has to be in the negative k hat direction, right? So the angular acceleration is very simple, because it's a 2D problem. Just take the derivative. K hat is unchanged, so only theta changes. So theta dot changes, and theta double dot is present as well. In general, it could be non-zero. It could also be a function. It may not be a constant. It could have any arbitrary value, but just that it's only along k hat. Now there are certain assumptions we make. One is about the wheel itself. Now about the center of the wheel. The center of the wheel obviously is the one where you can actually very clearly perceive the translation, though every point on the wheel is actually having the same translation. It's mixed up with the rotation at other points, whereas at the center, which also happens to be not only the center of rotation, center of axis of rotation, but also the center of mass, there you see pure translation there, so very easy to track that. And it's also useful for us, because we are going to look at forces as mass into acceleration. And then it's good to look at the acceleration of the center of mass. So it's good to set up these expressions up front, fairly straightforward. The velocity of the center of mass, of course, is just going to be given by your xc dot along your I hat. And acceleration is second derivative of xc, once again along I hat, no brainers there. Next, coming to the rolling constraint. The rolling constraint, as we already clearly saw, and you recollected in today's morning session as well, that it is equal to 0. So essentially we are saying the velocity of this particular point we are calling as p, the point of contact. Yeah.
And how we derive that the acceleration of that point is like r theta dot squared in the j half direction.
Yeah, good question. So you're saying that all points on the
Yeah, isn't that what we derived?
yeah, exactly. It is
So
true.
how is that for velocity?
See, there are two contributions for velocity at each point other than the center of mass. At the center of mass, it's only translational. Every other point has both an velocity due to rotation as well as velocity due to translation. Now, if you look at the point over here, it has a velocity of translation very similar to the center of mass. It's moving in this direction by vc. But then you also have, and that vc is equal to omega. And it, because it's on the rim at the distance r from the center of mass, it's also having a omega r velocity this way. So both are cancelling each other out. So it's omega r plus omega r minus omega.
Oh, I see.
Right. So the rolling constraint, therefore, is that the velocity of the point p, if it's a point contact, otherwise saying all the points on that line or surface, whatever it is, so is equal to 0. Now, constraint on the velocity of the center of mass and the angular velocity of the wheel is that they're kind of related to each other, because we're talking of rolling over here, and therefore they are related to each other. And this is what we just discussed. Xc dot is equal to r theta dot, right? So in other words, they cannot be independent variables. So in other words, it's a single degree of freedom system. Though it seems to be translating as well as rotating, both of them are related to each other. Theta and xc are not independent degrees of freedom. If you know one, you get the other, right? So your vc magnitude, the velocity at the center of mass, its magnitude, of course, is just r theta dot, and which is, of course, r times the theta dot being the angular velocity omega. It's the magnitude of that vector. And ac, the acceleration of the center of mass, again very simple, the next derivative of that. All of these, of course, are vectors. So the derivatives are with respect to an inertial frame of reference. Just keep that in mind. And that's why we already introduced that I over here. And the magnitude turns out to be theta double dot, which we call as we call alpha as the vector acceleration, angular acceleration vector. So it's the magnitude of that is theta double dot. Now, if you integrate this equation, obviously you're going to get a constant of integration, but you're essentially getting x is equal to r theta, and this is essentially set for this value of the constant by the initial conditions. Let's say to start with, you take theta and xc both equal to 0 at t equal to 0. That's how you define the datum or reference for both, and then obviously the constant goes to 0. Okay, or you could choose it for some other reason, some other value, non-zero constant as well. The whole thing will still work. Okay. Now the problem is about taking that forward, because what we looked at the kinematics there was for the horizontal surface. Now we are bringing in a non-zero inclination angle. So we call that beta here. I don't know what else over here. Let's see. So once again, the forces, all the forces involved, the gravitational force, the normal force, and the friction force, all are marked over here. Of course, we need to eventually break up that gravitational force into directions parallel and perpendicular to the path. So let's say the initial condition is that it's starting from rest, which means that that constant we had to start with, we are essentially setting that datum to be 0. And as I said, we will look at multiple possibilities here. So there are 4 possible cases that you can think of for a given body and for a given inclination. So the first thing is, of course, the simplest, where you do not have any friction and it just slips. It's like having a block which is going down. If you there are very interesting experiments which can be done. Do you know how mu is determined?
It's like by testing, right?
Yeah, yeah.
There's no way to
Correct.
like mathematically.
Absolutely. So it's essentially a property of two surfaces, irrespective of what materials they are made of, what masses are there, what radiuses are there, what shapes are there. Doesn't matter. It's essentially property of two surfaces. And one easy way, one simple way people measure that, it's also done in many high school experiments, is that you start with a mechanism where you can change this angle of inclination. You start with 0, you keep a block over there, and you keep on increasing that inclination up to a point where it just starts slipping. So essentially, that beta you can very easily show from these equations, equilibrium equations, that the tan of that beta is your mu. So you can directly by the tangent of that angle. So very, very simple experiment to do and to get those values, a good estimate for the coefficient of friction between any two surfaces, right? So frictionless surfaces, you would have slip. If you have slowly start increasing the roughness of these two surfaces, obviously there's going to be a friction which is going to come up, non-zero coefficient of friction, and once you have reached a certain sufficient level, rolling is a possibility. Until then you would have slipping, and slowly it could be a combination of slipping and rolling, and then eventually rolling without slipping will happen. Then if you have insufficient friction, which is what I said, in between those two cases, I should have probably put this before, maybe I should have listed this second. So insufficient friction will result in slip, and maybe and when you have an unknown level of friction, you will not know a priori whether it's going to slip or it's going to roll, and because you don't know what is that threshold, and you need to eventually determine that. So you could have you'll have to study for both cases and then arrive at the conclusion based on the results. Okay, and as far as whether something is sufficient or insufficient, initially we'll have to assume that, but later on through the results we can go back, revisit it and try to get it. But the third thing is, of course, this is the truth, that you really have an unknown level of friction, and this itself could become a method of measuring that. And so that's the reality, that in general you should be open to the fact that there could be rolling and or slipping.
So if you have insufficient level of friction, typically that's both slip and roll.
Yeah. So it all depends on like the threshold. So it's like what you call as frictionless and what you call as sufficient friction. Those are all kind of not very clearly defined things. So we need to, as he said, everything has to be experimentally determined. So next, of course, there are lots of tribological models where they look at the surface roughness and various parameters, how you describe the surface, two surfaces, and then try to arrive at theoretical estimate of that as well, computational numerical analysis, but more often than not it's an experimental determination. Now the cylinder or sphere on the incline with frictionless surface is what we'll look at first. It's essentially going to be slipping. Once again, the forces are near the normal and the weight. We are not yet talking about the friction yet. So now because it's frictionless surface, so therefore that force is not there. So we have only two of these sources, gravitation and the normal, which is essentially a reaction of the surface. So now once again, three equilibrium equations, because three are trivial. The other direction Fz and Mx and My are anyway 0 equal to 0 forms. So we don't need those three equilibrium equations. We need only these three, and we have only three unknowns, which are xc, yc and theta, and the yc again becomes quite trivial, and that can be left out as well. So this is what we end up with. The known parameters in this set of equations are, of course, what causes inertia and what causes the gravitational forces, which is essentially your masses and the moment of inertia about the center of mass of an axis passing through the z axis, which is parallel to k hat. Right. So then if you look at the forces, you can easily sum up. In fact, we already wrote those out. As far as the y direction is concerned, we already showed that n is equal to mg cos beta. So that's essentially what you see in this second equation over there. Very easily you can see what's happening in the x direction as well. It's mg sine beta in the positive x direction, and then there in that example we generally had a friction, but now we do not have any friction, so that's the only force, and that should be equal to mass times the acceleration or the rate of change of translational momentum, whichever way you would want to look at it. But the expression for that, based on the simple kinematics that we already introduced in a previous class and reviewed today, becomes just mxc double dot. The third equation is a moment equation. There is no torque being applied because we know that both the forces that are being applied, namely the normal and the weight, are passing through the center, and therefore they cannot contribute to a torque. So only two forces present and no both axis of rotation, therefore the left hand side becomes 0. That is summation of m about c about the axis z is essentially 0, but your right hand side is still there, that izz times theta double dot, because then it, you know, izzc is not 0 because it's not a massless cylinder or sphere that you're dealing with. It has a finite mass and it has a finite size, and therefore you do have a non-zero izz, which means that the other term on the right hand side, theta double dot, should be equal to 0. So the unknowns, if you're looking at all the equations before solving any of them, are xc double dot, yc double dot, theta double dot, and the normal force also. So we have only 3 equations, but 4 unknowns. But the other one essentially comes from the kinematical constraint, which says that this is not going over the plane, it's remaining in touch with the plane, so therefore your yc is equal to 0, and therefore that gives you your fourth equation. 4 variables, 4 unknowns, quite easy and straightforward to solve these, even though they are ordinary differential equations, very, very simple constant coefficient equations that you can quite easily solve. So once you do that, you end up first of all writing the equations in a standard format where you write second order ordinary differential equations with all your derivative terms on the left hand side and what it is equal to on the right hand side. So it's only x double dot and n which have a right hand side. N is essentially coming from this second equation that we have, which we already solved on the board in the morning session. So that's essentially what we have over there. So the others are quite simple to solve now. We can go ahead and do that. Just note that I called it beta over here, beta, and there it is phi. It's one and the same. So we are referring to the same variable as beta phi. So we'll stick to phi, which is what I have on the slide. So coming to the next case, first case was frictionless, remember. Now we are bringing in what we call, within quotes, sufficient friction, right? Sufficient friction, again, it could be either a cylinder or sphere, hollow or solid, doesn't matter. Once again, it's on the incline. Now, apart from the 2 forces that we had in the previous slide, which were N and mg, we now have a new force which is coming up, F. Because we know that it's going to roll down, it's going to act opposite to that, and this is of course what the road is exerting on the wheel. The wheel exerts on the road will be opposite, as we already discussed. So this is what, when we say sufficient friction, another way of saying it is that it's no longer slipping, it has started rolling. Okay, so the equations remain one and the same in terms of what we had, just that we have to have one more force which is coming because of the friction, and which is also not passing through the center of mass and therefore causing a torque. So your third equation will change as well. So one is your x equation will change because of the new force, and your mzc equation will also change because you now have a new term on the left hand side for both of these equations. So what you can very easily see, it's your mg sine phi, which is the gravitational forces component parallel to the incline. Then you have minus f because it's acting in a negative x direction. This is the positive x and positive y that we have introduced. So based on that, and these are all uppercase as opposed to the small xyz, that system that we had for the inertial frame of reference coordinate system. So these are essentially associated with this, what is body fixed over there, right? Body fixed in the sense fixed to the incline rather than the rolling body, right? So now here you have, it's just that that is also an inertial frame of reference, by the way. Any frame which is fixed to the plane of inclined plane is also an inertial frame, just that it is rotated from your eye. It's not that angle is not changing. Of course, when you perform experiments, you'll change phi, but it's a discrete experiment for different phis. You typically do that. So sometimes you could have a motor which is running and trying to increase the inclination, and you might want to look at the dynamics of the system as a whole. That is the ball and the inclined plane. You can study that as well. It's not much more complicated than this. In fact, the interaction forces would all go to zero over there, and so it will become even simpler when you're looking at it as a system. The normal and the friction will not be contributing to that. So coming to solving these equations, quite straightforward. So once again, very similar equations, only difference is that you have got that term over here minus f, and there is a term over here which is essentially f times r, and these are all scalar equations because we are writing it in the component form. So we're no longer dealing with f and m as vectors. We are dealing with certain dot products of those with the I and j in these directions, and therefore we can just list them as scalar quantities. Now you also see that if the friction force is along this, which is opposite to the relative velocity, then you see that the torque is going into the board, and therefore it is negative, and that's why you have this minus fr. And similarly, it's also along the negative x-axis, and that's why even in the first equation appears with a negative sign, right?
What's a negative I?
It's clockwise.
Oh, this one?
Yeah.
Yeah. See, because your theta, your angular velocity. Yeah. Yeah, you can either include it within the theta or definition, or you can put it explicitly. Is one way of writing it.
I saw it as like,
Yeah.
since it's clockwise. Is it not?
Yeah.
Oh,
No, see, essentially your rotation theta is in one direction, and your force, friction force, is also trying to create a torque in the same direction. So essentially their magnitudes are equal to each other. So either you can see both plus or both minus. It's up to you based on your sign convention. Okay, so just summarizing those equations for the same case, you just take all those terms, because now you have an additional force, and that friction force is in turn going to be related to the forces, the normal force, and then therefore the gravitational force based on the y equilibrium. We go about this, and then if it's, let's say, a disk, for example, you would have that factor k that we were talking about earlier is about half, which is the same as for the cylinder, by the way, because it doesn't matter on the length of the cylinder. Even a disk is having a very similar kind of a behavior as far as this particular problem is concerned. So we can very easily see that many of these things, once you try to solve, you will see your m's and r's and all will get cancelled with each other on either side, and you will end up with certain simple equations. So we have not yet gotten into the energy way of looking at it, where we add the kinetic energy due to translation and kinetic energy due to rotation, where we can get the same results through certain energy based principles as well. Here, of course, friction is involved, and friction is involved, it's a dissipative system, so you have to be careful applying the law of conservation of energy. You have to make allowance for that, right? So then when you try to solve it, especially if you look at xc double dot, which is of great interest to it, because that's the acceleration of the center of mass of the wheel. So if it's like a part of, let's say, a vehicle or something, it's essentially the acceleration of the vehicle, which is a very, very important term. And you see that it's just dependent only on the acceleration, which is anyway constant for all practical purposes on Earth's surface, very slight variations, and therefore you have only dependence on phi. The inclination of the plane is all that affects that, And similarly here also, if you look at the rotation, because obviously they are related to each other by that value r, so it's quite clear that the only difference between these two is the denominator r that you have. Once again, it's going to be a function of v, but it's very interesting to see that the acceleration, the translational acceleration is not a function of r, and it is the acceleration which is angular acceleration is inversely proportional to r. So this is something that you need to look at. Many a times in many problems it will be the other way around. So this is a strange situation where you have this kind of a behavior, right? So then normal and f. So this is again something which will be of utility later on in terms of the frictional force, what value it turns out to be. So now we've been harping on this about rolling and slipping in terms of sufficient friction or insufficient friction, etc. So we have to check for the friction sufficiency for pure rolling, and the cylinder or the sphere will roll, and you have the friction force non-zero and above the critical, only then it can roll, otherwise it would have slipped like a block just sliding down the inclination. So then once there is friction, as I said, you will have energy loss, which means that you can have dissipation and your conservation of energy will not hold good. Am I right in saying this, or am I making a blunder in saying this? I said there is friction, so there is dissipation, there is energy loss. So law of conservation of energy doesn't hold in this problem. So am I right, or am I? There is? Yeah.
There's
Yeah.
the energy that's is like still part of the entire
Okay. Okay.
system.
Okay.
Yeah, I mean, if you consider
Yeah.
that.
Well, it depends what you consider your system.
Exactly.
Yeah.
Just take
Because-
these stuff into account. I mean, yes.
So actually, it is energy loss if you don't count that as part of it, right?
Right, but you have to,
You have to.
because you're playing a law of conservation of energy.
Yeah. So it's not energy loss.
You're losing useful energy,
Yeah.
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 but that energy gets transformed into heat.
Yeah.
So the energy's still there.
It's still conserved.
It's just you're not.
It's just in a different form, not in the useful form.
Exactly.
That's our answer.
Okay. Good teamwork. Also, you have to look at, is there some, when there is a system, a closed system, whether energy is conserved or not also depends upon whether there's work done externally onto the system or not. So essentially there's an energy transfer taking place with the environment. So is there something like that happening if you just look at the ball as a system?
Well, I guess
Not
like,
the road, okay, just the ball or the cylinder.
there's
Well, no,
work
it's
being
still
done
con-
by like the earth. If you-
Yeah, there's
Yeah,
work
it's
being
done
done
by the earth
externally.
on the
And then there's the normal force as well. Technically.
Yeah.
So that energy.
That's
like-
work by the road economically.
Yeah,
Right.
that's for right on that road, right?
Okay, you're starting to think on the lines, but what is work? Work, how do you define it in terms of these forces that we talked about?
Force times distance.
Yeah, with what distance? You have to be more precise and
The
Like,
distance that the force acts on.
The force, no, the one that's parallel with the
Well, not necessarily. It's just
talk about.
it's
No,
just
no,
the distance that the force acts on that object.
Mhm.
So it's like whatever that distance is, that's what you multiply by the force to get the work.
Okay, I guess that makes sense. Wait,
The polar system
Yeah.
is the friction force.
so you are right. So you're talking of the dot product, right? So dot product of what and what?
Force.
space?
Yeah.
Yeah.
So it won't be displacement in any direction, right? When you have a dot product, dot products can go to zero if the angle between those two are, yeah, or if either one of them is zero by themselves or both are zero, yeah. So the trivial cases. Do any of these hold here? Yeah.
Gravity is
the
doing
angle.
gravity is doing some work.
Mhm.
Because friction is doing work because it's gravitational motion.
Yeah. So if you're looking at gravity, essentially it's stored in this system in the ball as a potential energy when it's on the top. So when it's coming down, that potential energy is getting converted to kinetic energy because you initially started with zero speed, so no kinetic energy, no translational or rotating kinetic energy, and then eventually you gain them, right? So you talked about two forces, normal and the gravitation. We have a third force. Is that doing any work?
Friction. Yes, because
Or is it consuming any?
Oh,
Yeah.
it's
Go by the same definition. Since definition dot product.
yeah. Since it's the opposite of motion, it's like it's negative.
yes, negative work. So that means work is going out of the system. Sorry, energy is leaving the system. Yeah.
Yeah. Yeah, that will be true. But you need to also consider where the friction is acting. What's happening to that location?
Oh, there is no, because it's not the same exact point, right? You're rotating, so it's the forces over different points. So it's not actually doing any work.
Wait, why?
Friction doesn't do work, remember?
No, it does work.
No, it
If you
does.
consider only the system of the ball, because the point itself is moving. So like once you rotate a
Okay.
bit, then there's no that.
Okay, I agree
force
that the
on
force is on each point, but how does that? So what were you about to say on top of that? Like, so now like
If you consider the ball as a system, the friction is not doing any work.
It's not doing because it's on.
it's not doing because it's rolling.
Yeah.
If it was sliding, then it puts it.
Yes.
Yep.
If it's sliding, then there's at least some that same point is being acted upon by the friction force. But if it's continuously rolling, then it's not.
Yeah, because it's the mathematical argument. What you said is physical, but mathematical is the same thing. You have F dot the displacement because your velocity is zero at that particular point. So
Oh.
if it is rolling without slipping, but if it is slipping, yes. Yeah. So if it is slipping, is it doing positive work or negative? Yeah, as you would expect, is a dissipation essentially. And mathematical argument for that is your F dot D. They are at 180 degrees to each other. Your cosine theta negative. Yeah. So this is what it is. So in this case, we are looking at pure rolling, therefore no slip. So there's no relative displacement between those two surfaces at the point of contact, and therefore no work is done when it is under pure rolling. So the system is actually conservative, very interesting, non-intuitive, because whenever you think of friction, you think of maybe there is energy loss. So no change, this implies that there is no change in the total energy. So you can solve the same problem by using the constancy of the kinetic energy plus the potential energy due to the gravitational field, and the kinetic energy due to two things, rotation as well as translation. Don't forget these two, they both have a contribution. Okay, sometimes one could be much larger than the other depending on the problem, but beware that both these contributions are there. So now we move on to the third case where there is so-called, within quotes, insufficient friction, right? So cylinder or sphere on the incline, once again the same problem, and we're not saying frictionless, in which case there will be only two forces, normal and gravitational, but we do have a friction force, but it's smaller than required for something. So what is that? So essentially we are saying that it's slipping, okay, when we say insufficient friction. Once again, the form of the equilibrium equations one and the same, two translational equilibria, dynamic, and one dynamic moment equilibrium.
Will this be slipping and rolling, or just slipping?
We'll see. Yeah. So we have to look at these equations. So what is the difference between this case and the previous case in terms of what is the contribution to the equations? The only change we have made, that is, we had sufficient friction, now insufficient friction, right? Yeah.
Okay, yeah, it could be less, right? That's what you're saying.
It can be less than.
Yeah,
I don't know
that,
how it is.
but how to,
Is it inequality?
Yeah.
Like the third unit equation, like f is less than or equal to
Mm-hmm. Mm-hmm.
wait,
whatever.
what did you say again?
I think that's true.
Wait, can you say it?
Like, since friction is less than or equal to m,
Okay.
fr is less than or equal to I.
Um, no, but doesn't the moment or the angular momentum directly come from that? So you can't just separate them and say they're less, right? Because it comes
No,
from.
it should be less than or equal to.
Well, if the friction, okay, the friction reduces to that, isn't that also going to change as well? Or no? It doesn't change? Because if you're saying if you put inequality less than, then you're saying the other part doesn't change when you reduce it. You gotta get sufficient friction. But I don't think,
Oh, I see what you're saying.
yeah, but I don't think it doesn't, I think it changes along with
When
it.
you're using I, beta double pi also changes.
Exactly, yeah. I'm saying then they're supposed to be related, right? So I don't, if you reduce it, the other one
I
should
mean,
be
it would make
reduced.
sense if you're slipping, you have less.
If you're
less
slipping.
acceleration,
I'm trying to think of
angular
this.
acceleration.
See, less, in reducing you have less.
I agree with that. Okay.
Less than radius.
Anyway, hold on to your thoughts because you will need some of these things when you solve your homework problems. We'll revisit this when we come back, and because that will be kind of giving a clue or hint to solving some of the problems. So think about it. Anyway, I'll be sharing these slides also as usual, so you can always take a look at that. Yeah. Oh, okay. Anyway, I'm going to give the slides. So look at it at home. This is your home. Anyway, so is the cylinder or sphere slipping in the, it's not only whether it is slipping or not, but also another thing that you have to do, especially with friction, is it slipping in the right direction or not? Okay, so because you have an incline, so it becomes very clear. But anyway, so you do take a look at this as well. You have quite a few problems on rolling as part of your assignment set, right? So yeah, and slipping. So angular velocity and angular acceleration is the next topic that we are going to get into. Of course, we have looked at these already from various perspectives. In the case of the 2D motion, very straightforward and simple, theta dot and theta double dot were your omega and alpha. But now when you're looking at 3D motion, these can get a little more complex, and that's where you need more stronger mathematical rigor in order to handle it. Okay, so again we'll start simply with simple rotation and what is also known as the corresponding simple angular velocity. So the word simple is used in a very let's say technical sense over here. It's not just like an English adjective of simple. There is a specific meaning we give when we say something is a simple rotation. So essentially is that you have found out an axis of rotation, that axis of rotation remains the same through the duration of motion that you are interested in trying to study this particular problem or the motion. So as always, we call that direction as k without any loss of generality, because we can introduce always our xyz coordinate system such that xy is in the plane of the 2D motion that is involved when you have simple rotation and therefore simple angular velocity, which is what is shown by the circle over here, and essentially that is along the A3 direction that you have. That's the positive direction that you have for that. Yeah. So we've introduced two sets of unit vectors, ij and the A1 A2 system, which is kind of rotating and as a function of time. The angular velocity is a vector, as we are aware. So far many a times we've been using it as a scalar because we had only one component which was non-zero, so we had the luxury of doing that. Not always, so you will have to remember quite often that it is a vector and use it appropriately, and the transformations also should take care of the rules for vector transformation. Now as is shown here, we consider two frames. The one which I hat and j hat are fixed is your inertial frame of reference I. The one which A1 hat, A2 hat and A3 hat are fixed, A3 hat being equal to k hat, is the frame A. Okay, for all you know, this could be the aircraft fixed frame and this could be the earth fixed frame for a lot of aircraft dynamics problems. Now the simple rotation, what we mean by that essentially is that this body A is rotating an angle theta in a given duration, let's say delta t, with respect to I, about an axis which is fixed in both frames of reference, both A and I. So that is what is the definition of simple rotation. This is not something that is peculiar to your book or something, which is it's a generally valid concept that is used in almost all of engineering dynamics. When we study rotation, we start by studying so-called simple rotation, where the rotation is actually happening about an axis which is fixed in both the bodies or both the frames of reference. That is the one which is rotating and the one with respect to which it is rotating. Both are having a fixed line which we call as the axis of rotation, and without loss of generality, as I said, we can call that direction as k hat or A3 hat. WLOG just as an abbreviation for without loss of generality. Yeah. Now what does this imply? The simple angular velocity of A in I. There are multiple ways in which this is written. So in some books, including your textbook, it's written as omega of A slash I. That means angular velocity of A with respect to I. But I usually prefer putting the I as a free superscript, as you know, on the left hand side, but it's up to you. Whatever convention you follow, just stick on to it for all times, because that's the convention we've been following for taking time derivatives, right? So here theta is not necessarily a vector in that sense, but from a simple rotation point of view, you can think of it as a vector. Also, when not large rotations are involved, what are known as infinitesimal rotations, then even if it is there in all three directions, all three orthogonal directions, you could still have an infinitesimal rotation vector. But once finite rotation kicks in, you cannot do that, and we will see ways of handling that a little later on. But now things are simple because it's simple rotation, simple angular velocity, and therefore you can write it as theta dot k, and the theta dot obviously has to be in your I frame of reference. But since both k hat as well as A3 are one and the same and remain a constant, really doesn't matter whether you take the derivative in the I frame or the A frame as far as this equation is concerned. So this is valid for simple cases, and chapter 3 is something that we already covered a couple of classes prior to this, but you can actually see that many of the problems there, in fact some of the homework problems that you already solved were also making use of these concepts without giving it those specific technical names. Okay, so in 2D, because it's a 2D motion, this is a scalar, that is your angular velocity, no longer a vector. You can call it an angular speed instead, and you can write it either as omega or a theta dot. Right. So next we go on to a mathematical definition of the angular velocity. So angular velocity definition. This is something much more mathematically rigorous and might look very difficult to perceive, but it's actually quite straightforward. If I just replace these d by dt's by dots, you'd see it's just b2 dot b3 dot times b1, and you're cyclically rotating that, going to the next term and the next term, so essentially covering the derivatives of all three unit vectors. Now what are we talking about here? We're talking about the angular velocity of frame B in frame A, or a rigid body B with respect to rigid body A, or one of them could be a frame of reference, other could be a rigid body, it doesn't matter. So essentially you're talking about that. So then what you do is you take the unit vectors associated with the frame whose angular velocity you're interested in, and take its derivatives with respect to the frame with respect to which you want to get the angular velocity. So all the derivatives with respect to time are with respect to A, but all the unit vectors that are there, none of them are A1, A2, A3, they're all associated with B1, the B1, B2, B3 is what you see over there. Now, it's beyond the scope of this course to kind of prove this and whatever. In fact, rarely will you use this. It's mostly for derivation of some of the stuff that this becomes very convenient to utilize, especially when you're dealing with what is not simple rotation, which is what we saw in the previous slide. This is the most general form of rotation that you can have, and a very simple way in terms of defining it in terms of time derivatives of unit vectors. And this is not after all very complicated. Remember, time derivatives of unit vectors we've been taking. We have d by dt of ER to show it is along E theta. We have taken time in the polar coordinates. So we took the time derivative of ER to show that it is along E theta. So we have done things like this. So it's fairly straightforward. And this is a dot product. And you'll be very familiar with the dot product. Once you make the dot product, the quantities within I compute within the bracket are essentially measure numbers, scalars, and it's just your omega vector has a B1 component, it has a B2 component, it has a B3 component. Each one of those are essentially dot products of how one vector varies, unit vector varies with respect to time in the other frame dotted with the second unit vector. Yes, Krish.
So when we have 2D motion, like say B is rotating, then a 2D, like it only has a k hat.
Yeah.
So how do the first terms go to zero?
Yeah, so you will have only this term.
Yeah.
So you will have the other two terms going to zero.
Yeah.
How do they go to zero? Yeah. So either because they are not changing with respect to time, or the dot product is going to go to zero. So when does the dot product go to zero? When they are perpendicular to each other. So you can see that the way B2 changes with respect to time, either it is not changing with respect to time, or it will be perpendicular to B3, and then you can easily see that these two, it's a good question you ask, because you can kind of really correlate with what you already know, so that way you learn this much better. Thanks. So this formula is useful, as I said, in derivations, but you rarely use it in actual calculations or to calculate the angular velocity, etc. Because you do not know the unit vectors a priori. But in many cases, it depends on the kind of unit vector system that you introduce. So sometimes it is possible that you can actually take these derivatives and take the dot products, and especially when you're dealing with intrinsic coordinates, the natural coordinates associated with the what we introduced, the tangential unit vector, the normal unit vector, and the binormal unit vector. So in that case, this kind of a definition becomes very useful, and a lot of structural applications when you're dealing with beams, etc. So this kind of equation becomes very useful. Now we get on to the addition theorem for angular velocity, something which we will very often use. This is something that is, this is kind of obvious, that if there is an angular velocity of A with respect to B, it should be the negative when you're taking the other way around, that the angular velocity of B in A. So if this body is rotating at a certain angle with respect to another body, if you sit on that frame of reference, you will actually see the other one is actually rotating in the opposite direction by the same magnitude. So which is essentially what this is. Now a little more advanced version of this, or generalized version of this, is to introduce not only live with the frames that you are interested in. One is the body, the other is the frame with respect to which rotations, but introduce a second or intermediate frame in between them, the third frame. So, or even third, fourth and fifth sometimes, especially when you had multiple systems. Many of you worked on these 4-bar mechanism problems where you had bar 1, bar 2, bar 3. So each of them was rotating. So you could have the angular velocity of one with respect to the inertial, then you could add up and get to the other. So many of these things you have been doing kind of intuitively, but there is a lot of mathematical rigor behind it as well, a basis. So this is the addition theorem for angular velocity. So first we consider just two frames of reference to start with, A and B. We are interested in the angular velocity of one with respect to the other. Then because they are kind of complicated the way they are connected to each other through various kinds of joints, some revolute joints, hinges, etc. And there might be other rigid bodies which are coming in between. So you might want to, you can think of A and B as bars B1 and B3, the two vertical bars, and then there's a third bar which was connecting them. You can think of that as C, for example, right? So it's something which is coming intermediate. Many times it may not be an actual physical body. You might introduce an auxiliary frame of reference just to make your derivation much simpler. Okay, so that's what you do. Once you do that, the angular velocities are kind of very easily related, and it follows a very simple rule. If you want angular velocity of B in A, first get to B to C, which might be much simpler to deal with. Each of these might be a simple rotation, whereas this might be a complicated 3D rotation. You can break it up into possibly simple rotations. Not necessarily each of these could also be 3D rotations, but eventually many of the times this formula is used is where you can break it up into smaller rotations. So what you're saying is that instead of directly going from B to A, I go from B to C and then from C to A. Okay, so you're having some intermediate stop junction in between, so that expressions become much easier to derive, and then you just add them up to get what you are interested in. And from this you can also very easily see that this will hold, because if I take this to the left hand side, the right hand side of this red equation, I take it to the left hand side, AB to plus BA. So essentially you're coming back to the same place. Obviously it has to go to 0. No angular velocity involved. Now, addition of multiple simple angular velocities, that whatever we presented in the previous slide was valid for any angular velocities, not only simple angular velocities, but it becomes much more useful and powerful, this method, when you employ on the right hand side all simple angular velocities, each of which excuse me, you can derive very simply, and then you can just add them up to get to the overall angular velocity that you are interested in. So the addition theorem therefore is very, very powerful, and it's common to determine angular velocity of a rigid body as a sum of two or more simple angular velocities, each of them having an axis of rotation which is common between the body and the body with respect to which it is rotating, which is what simple rotation is all about. Next, coming to differentiation in two frames of reference that you're already familiar with. Let's see how that kind of operates over here in this concept. So for any vector q, you know that if you want the d by dt of that in an inertial frame, but it's very complicated to get it in the inertial frame directly, you get it in another frame A, and then you get the cross product of the angular velocity of A and I crossed with q. You have amply applied this particular rule for a lot of your problem solutions, right? Now, problems where you have applied it to include where the q is any arbitrary vector, but it should take on the form of a displacement or a velocity or an angular velocity, doesn't matter, you name it and you have it, or any arbitrary vector which doesn't even have any physical meaning. Now, very important relation used frequently, this particular relation, and you already know that how frequently you have used it. The angular velocity, of course, is the key to this, and this angular velocity will be in terms of that etc. cyclically, two more terms, and that can come over here, and you could see how much powerful this will be when used for arbitrary 3D rotations, which are usually very, very difficult to handle otherwise. So angular velocity is key to differentiation of vectors in rotating frames of reference. in addition to giving info, of course, about the rigid body's angular motion itself, which is what angular displacement, or which is rotation, or angular velocity, angular acceleration, all some information about how the rotational motion of the rigid body is taking place. It could be used to calculate either the angular momentum of it or the rotational kinetic energy of it, etc. But in addition to that, they are helping us to take derivatives, which is a very, very powerful device or tool if you are using angular velocity in that manner. Now, we also know that many cases this specialized form of the same thing is used, where Q is not changing in the frame A, and therefore the first term drops off, and therefore essentially you're replacing an I d by dt, a differential operator, with just a cross product operator with the angular velocity. So that's the power of the angular velocity. It's essentially doing differentiation for you without even having any calculus on the right hand side. It's just a linear algebra on the right hand side. Left hand side you have a differential calculus. Angular acceleration is something we go to next. So because we looked at angular velocity, we might be tempted to think that there is something called a simple angular acceleration and addition of angular accelerations, etc. But we are in for an unpleasant surprise there. So consider two frames of reference once again. Earlier we were talking of angular velocities. Now we are talking of angular acceleration between these two frames of reference. So the angular acceleration of B in A can obviously be obtained by the time derivatives that we are familiar with in the velocity spectrum as well, where we used to say the translational acceleration is given by the time derivative of the translational velocity in an inertial frame of reference, for it to be useful later on to be taken for the Newton's laws, etc., which are valid only in inertial frames of reference. But you can take angular acceleration of any body with respect to any other body, which need not be an inertial frame of reference also. Same thing in the case of the angular velocity also. When we are talking of frames B, A, C, etc., there was no limitation for those results to hold if and only if some of those are inertial frames of reference. No, they could be either inertial or non-inertial. Some of them could be inertial, some of them non-inertial, doesn't matter. Okay, so you could always use those equations, and similarly this equation also of the angular acceleration as a derivative of the angular velocity. Now you can substitute that b1 dot b2 times b3, etc., two more terms into this, and you can get an angular acceleration in terms of b1 double dots, b2 double dots, and b3 double dots as well. Okay, so that is one way of approaching the problem. The other, of course, is in terms of decomposing this into simple angular velocities, sums of that using the addition theorem that we just looked at, and then take the time derivatives of each one of them. Okay, so now we employ the equation that we revised or reviewed in the previous slide, which is the time derivative equation, which can be written as just an angular velocity operator equation. So we can very easily do that. If you want the time derivative of the angular velocity, which is what is required in this definition, I can just take it as the time derivative of the same angular velocity in the body itself. Whichever body's angular velocity we are interested in, we are taking the time derivative with respect to that. So it's omega of b in b, the time derivative also is in b, and therefore you have the second term very interestingly becomes the same, omega va cross omega va, because of the specific choice of the vector with which we want to use that 2-point fixed on a body formula. So the second term obviously is a cross product of the same quantity, it goes to 0. You're ending up with saying it doesn't matter whether I take my derivative with respect to time either in frame A or in frame B, I'm going to end up with the same result, which is the angular acceleration of B in A. Sometimes it might be easier to take in frame A, sometimes it might be easier to take in frame B. You have the choice to do it the easier way. Okay, so that's of course the result. That doesn't matter. So we've always been harping, it really is important that you specify the frame of reference when you take the time derivative, because it can in general be different, etc., etc. But here is a special case where these two are equal to each other, irrespective of whether the derivative is taken in frame A or frame B, even though the same vector's time derivative is on the right hand side. Now to calculate the angular acceleration of B in A, that is alpha BA, we have to differentiate, of course, the angular velocity of B in A in either frame of reference, that is either A or B only. Of course, these two are the only choices. You can't say I will do it with respect to C, it's even more easier to do it with respect to C. So for this it will not work. So only when the angular velocity of C is involved, so then you have to do that. Here it is angular velocity of B in A. So the two choices with respect to which you can take the derivative without any change is either A or B, not in a third frame of reference. Okay. So usual differentiation formula to differentiate angular velocity in all other frames of reference as well. So the differentiation formula that we used is essentially what you use in other frames of reference as well. Next, this is again, as I said, another unpleasant surprise that you have as far as angular acceleration is concerned, that it is not additive. You don't have so-called simple angular acceleration, one shock. The other shock is that you can't use the addition theorem over here. So the end result I'll show first, and then we will see what it is. The end result, of course, if the boxed terms were not there, only up to here, it is very simple to, similar to your angular velocity addition theorem, where you're just, instead of going directly from B to A, you're going from B to C and then from C to A. But these are not the only two terms. There are additional terms in the angular acceleration, which involve a cross product of angular velocity of C in A with angular velocity of B in C. So it's essentially these same quantities, but not accelerations, but angular velocities. The units, of course, are the same because omegas have a 1 by time, it's radian by time. So whereas these are radian per second squared, so you see that there are two omegas here, and therefore we'll have a 1 by time squared dimension for this as well. So why?
Does it like that Coriolis effect that we previously had?
Yeah. Oops. So now we consider two frames of reference, A and B, and an auxiliary intermediate frame of reference as well, because we want to prove that that formula doesn't work, but it does work for the angular velocities. So that formula is what we start off with. Then it's very easy to go from that to the angular accelerations, because you know angular accelerations are defined as just the time derivatives of that, and you also have the freedom of whichever frame it is easier to take the derivative. You can take either with respect to B or with respect to C for each term that holds, and we end up doing that. So your angular acceleration of B in A, for example, that is the left hand side, is equal to AD by dt. I could have as well chosen B, but if we choose A without loss of generality, then I end up with your sum, because I can just substitute the first equation in the second, then I end up with this. Then what happens with that? Now I start applying the 2-point formula for arbitrary vectors. You know that you can introduce the angular velocity operator. So you do that for your omega BC. Instead of taking derivative in A, I take it in C. And when I do that, I should get this cross product as well, and keeping the other term as it is. Now you see that these are nothing but your definitions of the angular acceleration. So I can substitute the first and the last terms over here, and then I'm still left with the middle term, which is a cross product between two angular velocities. So this is the one which is causing the issue, and that's what is over here. Okay. So feel free to apply the addition theorem with angular velocities, but be cautioned about not using it for angular accelerations. If you do, make sure you add this third term as well. If it's just one intermediate frame, for each such intermediate frame, you will have one more cross product getting added up over there. Okay, so that's as far as angular acceleration. Some notes on the notation. I've been harping on sticking to certain notations, at least for this class, but it's a good practice that you can develop for your work beyond the course as well, in terms of sticking to these notations, because it avoids confusion. But many a times you'll be dealing with very simple problems, and you'll feel like, why am I carrying all these subscripts and superscripts and all that? It doesn't make sense. There's a default, and everybody understands what it is. So yes, common not to include that. You see that in fact a lot of literature as well as books that they're dropping off all these and subscripts on angular velocity or angular acceleration if the meaning is obvious. Obviously the left subscript on time derivative if the meaning is obvious once again. So similarly those can be dropped off as well. But do keep in mind that the problems that you're solving as part of your homeworks, etc., are part of your learning pedagogical part of your journey, where you're actually, even though it might seem like complicated, it's actually, there are fairly simple problems compared to real life problems that you will face in aircraft dynamics or spacecraft dynamics and various other such, not courses, but in the industry when you go, and you will involve many intermediate frames of reference, many points, many rigid bodies, very complicated shaped rigid bodies which can be decomposed into a very large number of special shaped rigid bodies, etc. There you will see the real power of holding on to your notations, because most of the time you're not going to be doing this by hand. You're going to let a computational algorithm do it for you, and precision is very important in defining those variables so that there is no room for whereas a human mind very easily it recognizes something even without a proper notation, that's what it is, it's the default, so I know what it is. But many a times the computational algorithms will not be able to do that, and they could sometimes have lots of huge errors which could be quite disastrous. So it's important that yes, for doing simpler problems you can sometimes do that because it reduces your writing time as well as the clutter on the page. Things look much simpler and compact when you drop off all those subscripts and superscripts where the default value is there. But as I said, when you go to real life problems, it will be confusing, and especially for algorithms. And now, as you know, we are moving into the AI realm, which is the new normal, and there you really need a lot more appropriate prompting, at least at the stage at which we are with AI. Maybe things will become much more human-like a few decades later, but as of now, any small error that you have in the prompt can completely change the answers, because the way the computer understands what you are asking for could be very different. But if you have precision in terms of how you express these things, then you would see that more often you will not have an issue.
I just want to confirm that the left superscript is like the reference for rectangular images, right?
Yeah, so that id by dt, ad by dt, etc. Yeah. So sometimes the only frame that you have chosen is the I frame. So every derivative is with respect to I frame. So why should I just keep putting id by dt
But
every
if I
time?
have like w dot or like theta dot, do I still include it? Or
Yeah, so it's a question of scalar. So once you have gotten into a scalar and you have defined that scalar as a particular measure number of a vector, even though it was a part of a vector, because of the new definition that you have given for an intermediate new variable, so you can do it without that going forward. But when you are writing it as a vector, very important to retain the complete notation. Yeah. So I can define, for example, that omega b a, the second component of that as just omega 2. And everywhere I can continue with that omega 2 because I have defined omega 2 as omega b slash a dotted with b2. Okay, so that's that. Then the 2 points fixed on moving and or rotating rigid body that you are very familiar with, these 2 points P and Q, and then therefore the angular velocity on which these two are fixed comes in as a cross operator. And I keep repeating this because many a times people get confused that it should be either only on the surface or within the body, etc. No, it has to be somewhere associated with the body such that it is moving with the body, doing whatever the body does in some sense, so that it's kind of an extension to the body, that particular point, and therefore you can still apply this, and which is what makes it so much more powerful than just applying to some points specifically on that particular point, right? So it's on, in, or with respect to. So that's all three are valid as far as this particular equation is concerned. So the velocity of one point of the rigid body is known, that is essentially your VQ. Then you can get the velocity of another point, any of its other points, using the same rigid body's angular velocity. By same rigid body I mean the one on which P and Q are fixed or associated with. Now, the reason why, though you know these things, I'm bringing this up is because something that we are going to introduce is very similar to that. So it will make the understanding of that much easier. So 2 points fixed on moving and or rotating rigid body. You have P and Q, which are fixed on, in, again, on or in or with respect to rigid body A. Then we can get into the accelerations. In fact, we have done this before, but now we know that it's not as simple as the velocity. You have an additional term, and essentially you know that this is your centripetal acceleration that is coming in over here, the omega cross RQP, with the second cross product having to be taken first. So then, of course, you have an alpha cross RQP. So this is many a times called as the Eulerian acceleration term, just like this is centripetal acceleration term. This is very common in the literature too, if you see that this is called as the Eulerian acceleration term.
How does that simplify to the equation that we use?
Omega squared R. Yeah, so you see in the simple rotation case, this is k hat, this is k hat. So k hat cross r hat will give you theta hat with a negative sign, and k hat cross theta hat will give you r hat.
Oh, I see.
And already you got a negative sign, so that's what made it centripetal rather than centrifugal.
But in general, this is the correct form of it.
That's correct. Yeah. So this is the more general one. So then you start because that K version is just for 2D rigid body motion, whereas in general you can have your omegas along all three directions, as we saw that formula B1 dot B2 times B3 and two more terms. This is what you substitute here, and you can get the most generic form. So if acceleration of 1 point on or in or with respect to a rigid body is known, you can find the acceleration at any other of the same rigid body's points using the same rigid body's angular velocity as well as angular acceleration. So you see that omega is appearing here of the rigid body and a particular inertial reference frame, and then you have the angular acceleration alpha also appearing here. Both are acting as operators in order to simplify the acceleration calculations. If you're going from the first principles of taking the time derivative, that might be sometimes much more complicated than just using this, because you might already have expressions for your omegas and alphas. You might as well utilize them. And you might know the acceleration of 1 point, which could, for example, be the center of mass. Then you know the acceleration of any other point on the same body. Okay, now we want to look at velocity and acceleration in moving or rotating frames of reference. So this is what I said, even though we had studied earlier, I'm just revising that because we already have that equation. Now we will do something very similar, but much also very powerful equation for and different application. Many a times these two will be used in conjunction. Both of these equations together can totally simplify some very complex looking problems. So it's very important to remember that. So we already have, what we already have is for V and A of 2 points fixed on, in or with respect to a rigid body. Now what we are going to do, not fixed but moving, okay, and only 1 point. So it's 1 point which is moving on in with respect to a rigid body. You can think of it, let's say a train is moving and you're moving within the train, or the train is taking a circular path, or if, let's say in a ride that you're going through, you're making certain motions, or the cart that you are sitting on is making certain motions, etc. So there are certain points on the rigid body, so-called rigid body, which are essentially moving. So then once you have something which is moving with respect to that rigid body, which is associated with that rigid body, and you know how it is moving with respect to that rigid body. I know how I'm moving within the aircraft. Now I know the aircraft's motion with respect to the earth. So I can get my motion with respect to the earth on the aircraft. So that is essentially the kind of connectivity that we want to draw. That might seem like a silly example where you probably don't have much value for it, but there are certain cases where you would see that those are very, very critical. For example, if your astronaut is taking a spacewalk, so the spacewalk, while taking the spacewalk, you know how the astronaut is moving with respect to the satellite to which he or she might be tethered. But then what is really matters is in terms of with respect to an inertial frame, what are the forces and moments acting on his body, because that will give you the G forces, whether he or she will be able to withstand it or not, and things like that. So certain maneuvers or certain operations that they would do in a spacewalk might be kind of dictated, and they might be trained for that a priori in order to avoid issues later on, right? So, so many such examples you can think of in engineering as well, and you will see some of those in the problem sets as well going forward. So now we derive expressions for V and A of one point moving on in or with respect to rigid body. So let's go about doing that. So this is the inertial frame of reference, which we call as I, with an origin O, and then we have a rigid body over here, and we have another frame of reference associated with the rigid body B, and that has an origin O prime. And now we are tracking one particular point P, which is moving with respect to the rigid body, and I know how it is moving with respect to the rigid body, but I want to know how P is moving with respect to I. So that's essentially we want to develop a formula for that. We have all the knowledge in order to do that. It's just a matter of putting them together, which is what we will do here. So we know that to start with, let's assume instantaneously that particular point is at a given location on B. So while the P itself, as P moves on, will go to some other location, I'm just tracking that particular point at which it was at that instant in time. So that's essentially what you're trying to do. So when you do that, if point P were fixed in the frame of reference B, then you have the velocity of P in I, which is what I'm interested in. That is going to be the velocity of O prime in I, O prime being that point which was the origin of this frame, and then plus an omega bi cross with r O prime P. So this is something we know. So this is something based on what we already know of 2 points, because these 2 points P and I at that particular point are fixed and instantaneously, and I can apply that particular formula, but it will not hold once P starts moving. That complication will come up. So how do we deal with that? Now what if, as I said, point P moves in some way within the frame of reference B? In other words, the velocity of P in B, what we call as BVP, B being a pre-superscript and P being a postscript, you will see that what if P moves in frame of reference B, that velocity is not equal to 0, right? Now given point P's velocity in the frame of reference B, because we know how P is moving with respect to B, can we find its velocity in the frame of reference I? So that's eventually what we are trying to get into. Oh, I forgot to increase the font size. Okay, so all that we do is to bring in certain vector addition to start with. So going from O to P, because remember that the velocity of P in I will be in terms of the derivative of that vector, okay, of that any point whose velocity you are interested in, from a point which is fixed in the frame in which the velocity has to be determined. So we want to get ROP, but we can get ROP by first going from O to O prime, that is going from one frame of reference to the other frame of reference's origin, and then from that we want to march on to P. So it's just a simple position vector addition that you have over there. So now, therefore, your velocity of P in I is nothing but the time derivative of the left hand side of the top equation, but that derivative has to be taken in I, then only I will get the velocity in I. Because I want the velocity in I have to take the time derivative in I as well, and when I do that, substitute, I get straightforward those two things over there. Now the derivative of in I of ROO prime might be well known, because typically you will choose O prime, for example, as a center of mass of the body, or some point whose movement you can actually track. So you will typically have a knowledge of that. What is the other thing? That again, you know how the point is moving with respect to the rigid body. So P is how it is moving with respect to the rigid body, but you do not know how it is moving with respect to I. So you have to break it up into using the formula that you already know for how to take the time derivative in one frame, how to relate it to a time derivative in another frame using the angular velocity, which is what we are doing over here, right? So we are just replacing this first term, recognizing that as a velocity of O prime in I. So we are putting that there. And now this one, we are using the formula that we already know, which we just reviewed, where we are taking the derivative in one frame is equal to derivative in another frame, then angular velocity of that frame, new frame, crossed with the position vector. So which you are taking, and therefore you get this particular equation. Now things become much more familiar. The first term is nothing but a derivative in B, not in I, but in B, O prime P, and O prime P is this, and I know how P is moving with respect to B, so that becomes the velocity that I am already aware of, so I take that. Now I know already the overall motion of this rigid body includes the translation of its center of mass, which could be O prime, and then also its rotational motion, which means that I know the angular velocity of B in I. All that I have to do is cross it with the vector from O prime to P, which I can easily do. So once I rewrite that, now you can recognize this term also as the velocity of the point P in B, which is what is written over there. So we have a sum of two velocities now, and then a cross product as well, right? Now the velocity of P in I therefore can be written as, I'm just interchanging these two terms and putting it as velocity of P in B, and then the velocity of PB in I, where that PB is nothing but a point which is instantaneously fixed on B at the same location where P was at that instant in time. So that is essentially what this term turns out to be. So that's the simplification, that if I know the point at which it is at a given instant of time, I can take its velocity with respect to I, and then I can add that to get this. Okay, so now let's go look at it term by term. That VPB is already there, so that's not something that we are worried about. So what is this new thing that we have introduced here is what all those additional terms that were there, the first and the third term that were there in the previous equation, right? So we are defining this VPBI, or this new point PB for that matter, as such that the velocity of PBI is just the sum of these first and third terms. What does that actually do? We are saying that the velocity of PB in I is the velocity of O prime in I plus the angular velocity of B in I crossed with the vector from O prime to P. Now this P is the actual P which is continuing to move, whereas this is the particular point that we have fixed at that instant in time. So in terms of that, we can now get the velocity of P in I. Okay, so instantaneous velocity, so writing the same thing in words, you are essentially saying that it's the sum of two things. What we are interested in is the instantaneous velocity of P in the inertial frame of reference. So it's the inertial velocity that we are interested in of a point which is moving on a rigid body. So how do you get that? You get that by adding two quantities. The first quantity that you want is the velocity of P in the frame of reference B. You know how the person is moving within the aircraft, so you know the velocity of that. So then you add to that the velocity in the frame of reference I of that point PB, the new point that we have defined just now, which is fixed in the frame of reference B and coincident with point P instantaneously at that particular instant. At different point in time, a new point of B is going to be coinciding with P, and then you have to track that. So essentially it might look like kind of convoluted at this point in time, but once you start applying to problems, you will see the power of this particular method is almost as good or even better than the other equation that we have used over here in order to derive this particular equation, because it kind of contains the power of both within itself, because it's using the that 2-point fixed formula in terms of O prime and PB, and it's also using that P which is moving away from that PB to a different location, PB being an instantaneous location for that point. Okay. Yeah. So next is we look at in acceleration in a moving frame of reference. So in other words, we have been looking at inertial accelerations, but we also sometimes might be interested in what is the acceleration in a moving frame of reference. Okay. So if a point P is fixed in any frame of reference B, like the point that we were talking about, which was moving in B, now a point P which is fixed in B, then we know that this equation holds. We've been seeing this equation for velocity quite a few times, but acceleration also something that you have used earlier. So it just has an additional term, as I've been talking about. This is centripetal acceleration, and this is the Eulerian acceleration. Yeah.
This question also applies to the last example of the velocity. But, does the frame of reference B have to be inertial as well?
No, not necessarily. Doesn't. Yeah. So your aircraft can be accelerating and still it will hold. Yeah. It you can still use it when it's inertial, but it will become much simpler than what it is.
But I has
Yeah.
to be.
Yeah, sorry. Yeah, so we had this equation already. This is something that we know. Now, if not, then in other words, if P is no longer fixed, that is essentially you're talking about the problem that we saw in the previous slide, where we derived the expression for velocity. Now, this is the expression for the acceleration as well. So, just like we had the velocity expression for both velocity and acceleration of 2 points fixed on a rigid body, we have both expressions for velocity and acceleration of a point moving on a rigid body, right? So this is the expression that we have over here. Looks kind of complicated, but if you look at each term individually, you will kind of start recognizing that those correlations with what we have been talking about in terms of the centripetal, Eulerian, etc. But we can simplify this. So this is the simplified form of that. So once we simplify that, we can cross-verify. It's quite straightforward based on what we have shown in the previous slide. So we want the acceleration of a point P, which is moving on a rigid body B, in the inertial frame of reference. All that I have to do is to know the acceleration of that point on the rigid body. I have to add that to the acceleration of that instantaneously fixed point on B, at which the moving point was located, and that has to be an inertial acceleration as well. So that's fairly easy to get using typically the kind of formula we have on the first line. And then the third term that you have, so it's essentially just three terms of the acceleration. The third term that you have is a cross product of the angular velocity with the velocity. So what kind of acceleration is this? Any takes? Excellent. Yeah. So because you typically have two single derivatives, which is one is an angular velocity, which has a first derivative, and the velocity, which also has a first derivative. So the combination of that as a cross product is Coriolis, and you typically in a Coriolis you have a factor of 2 as well, which also you see over there. So that's essentially what it is. So this is actually a very, very powerful tool, because otherwise, without knowing this, if you go from first principles to calculate the inertial acceleration of P, which is a point moving on a rigid body, and the rigid body itself is translating and rotating in an arbitrary way, it's going to be much, much more difficult and time consuming and a lot more steps involved. Whereas if you just apply this, you will see that just these three quantities are required, most of which are already known in some form or the other in the question itself, or a little bit of using of the earlier equations for acceleration of 2 points fixed can help you to get most of these terms. So what does this say in words? So instantaneous acceleration of the point P in a frame of reference I is equal to the acceleration of the same point P in frame of reference B, which is of course APB, the first term. Then the second term is that you have an acceleration in the frame of reference I of the point PB, which is fixed in the frame of reference B. So that is what is the new thing you might want to get used to, because it's a new concept we introduced in this class. It might seem a little strange, but it's quite obvious. It's just that there's something which is on the rigid body, but instantaneously wherever it is located, that point of the rigid body I'm tracking. That is what I'm calling as PB. So it becomes once you start solving problems associated with that. So that is your second term, acceleration in the frame of reference I of the point PB fixed in your frame of reference B and coincident with P instantaneously at that instance. That's very, very important to remember, because that's something that we have not used before and you might miss that point. That's why I'm re-stressing that, also underlining and keep giving you in bold font. And as Kush pointed out, that last term is the Coriolis acceleration. Okay, I think this is a new topic which will take a longer time, so I'll probably cover it in the next class. Yeah, thank you.